Okay, so lots of stuff happening here. Today is right there. Okay, so Friday the 13th, there is a quiz due today. So go ahead and put the quiz in your folder right now. Thank you. Okay, and then the other thing that's happening right now is you are picking up the new quiz. This was the one that was not in the syllabus, but just announced the other day. So grab one of the new quizzes. You can look at it. The problems are all in your textbook. So the page really is just the rules. You're going to do the problems elsewhere, okay? Everybody has a copy of the new quiz? New quiz is due the Monday when we come back. Also due the Monday when we come back is project number 4, the gamma function, okay? Yep. That's what the snow days did. It would have been due Monday this week if it weren't for the snow days. What can I do? This past Monday is when it was. Oh, you're happy with the snow. All right. So today we're going to be starting a brand new topic. We're going to talk about areas and volumes. We've done some stuff with areas before, but I don't think we've done any volume work. But you can see the word volume popping up over the next 3 classes. So Eli had asked about, does the number of classes have something to do with the importance of the topic? And yeah, so apparently volumes are pretty important for us. We're going to be spending 3 days on it. And then after we do this little mini thing on volumes, we're then going to do a bunch of applications of the integral. There's some physics stuff, there's some economics stuff, there's some probability stuff. So a few different applications of the integral are coming up after break. Any questions on the calendar? Okay, so again, we're on page 30, and at the very start on page 30, number 1 just talks about the gamma project, which is this one that's due coming up right after the break, and it says that questions 5 and 8 are particularly tricky, and I want to give special notice to question number 8. I think number 5, you guys are in a good place to handle. Not to say that it's easy, but it follows pretty closely with what we did last class. But question number 8 involves using a technique that we really haven't used before and won't ever use again. And to be honest, when I first did this project, I got it from my predecessor. I did everything up until number 8, and I said, I don't know how to do this. I'm trying to compare, but the inequality was always going in the wrong direction. And so I had to call my predecessor. He was out in some other state. Hey, Curtis, how do you do number 8? And then he shared it with me. And so now Caitlin has a video that we're sharing with you. And that's the URL. It's also in our playlist on Moodle, okay? So I encourage you to take a look at that video as you get closer to doing 5 and or 8, all right? Any questions? The URL is in your packet. Yeah. Okay, so let's start with our daily summary up here at the top. Can we go to Isaac for the summary? Okay, thank you. So we're going to jump to number 2, but before we do, we're going to have a little flashback here. And I'm going to project something that we covered way back on the 2nd class of the semester. And this is our review day on integrals. And the problem was to find the area of this space under the curve and above the axis between these 2 vertical lines, right? And we decided we were going to cut this interval between A and B into a bunch of equal pieces, and then we drew a bunch of rectangles, and then we found the areas of those rectangles and added them all up. And then finally, we let the number of rectangles go to infinity. Yes? Okay, and then we decided we were just not going to write all of that crazy notation. Instead, we said, hey, whenever we mean area under a curve, we're just going to write an integral sign, right? And so we had on the next page here, our definition for area was this crazy looking limit here. Limit is the number of rectangles goes to infinity of the sum of the areas of all of our rectangles. F of t sub I, so the t sub i's were just counting out our rectangles, just enumerating them, and F of t sub I was just the height of the rectangle, delta t was just the width of the rectangle, so width times height gives me the area of one rectangle. We added them, we sent the number of rectangles to infinity, and we got tired of writing that, so we just decided we were going to instead write this symbol with the integral, okay? So they were equal to each other, that was just us defining that symbol. So we're going to use that today. And so I've written it over here just so we have it in front of us on the whiteboard. But anytime we see one of these crazy limits with sigma notation, we might be able to rewrite it as an integral, okay? It might not necessarily have the same area interpretation it did before, but if you see a limit with a sigma and it looks exactly in the right form, you can rewrite it as an integral. And I've got little colorful things here telling you what becomes what. So that limit and the sigma basically become the integral sign. the A and the B don't appear here. They have to appear in the problem someplace. The f of xi became just f of x, and then the delta x became dx, all right? So those pieces all become pieces over here. We're going to be looking for stuff today that looks like the left-hand side. All right, so number 2. Let's go to Ryan. Okay, you can pause right there. All right, so here's the picture, giving credit. This was just scanned from your book. And we're going to find the area of this thing. Okay, this is not a calculus question. What's the area of that triangle? Half of 3 times 6, which is 9. All right, so you're going to really appreciate that half base times height formula, given how complicated we're about to make this easy problem. Only right triangles. Well, no, actually, the base times height formula works for every triangle, but it was only easy to know the height because it was a right triangle. Yeah. Okay, so we said the area is 9. All right, so we're going to get 9, but it's going to be a long while before we get to the 9. But it's going somewhere good, okay? So here's what we're going to do. We are going to take this triangle, we're going to chop it up into little rectangles. Now that guy is a trapezoid, but I'm really thinking of it as a rectangle. It's going to be close to the right area, but it'll be too big or too small by just a little bit. And we're going to imagine taking that slice and having a bunch of slices, a bunch of rectangles. And then we're going to add up all the areas of these rectangles and take a limit and hopefully get the same 9 that we got before. Okay, so let's start writing some stuff. So area of one rectangle is how we're going to start. And I want to find the area of that rectangle right there. So we know area of a rectangle is base times height. The base is given in this problem. Do you see the symbol? Is the delta x. It's an appropriate symbol, right? It's a little change in x down there. Okay, so then the base is delta x. And the height, I'm just going to call h. At the moment, I don't know what it is. But once I find it, I can slap it down here next to my delta x. So that's a blank at the moment. So we got to come up with a way to rewrite that h thing. And the letter that I want to use is this x right here. X is, in this picture, that distance. And so I'd really like to figure out what h is in terms of x. Okay, so do you guys buy we have similar right triangles here? The big one compared to this little guy out here? Okay, so then we can use similarity to say that what, h over 3 is the same as x over 6, buy it? Right, those pieces are all in corresponding parts, corresponding places. So that means that h is really 3x over 6 or half x. So the height of that little rectangle there is half of x. Agree? Okay. Great. So I've got my area of the one rectangle. It's delta x times half of whatever that x distance is over there. Super. Again, we said we were going to take that triangle and break it up into a lot of rectangles. And I'm going to take the areas of all those rectangles and add them up. So then I'm going to say the area of all the rectangles. Okay, so all the rectangles. How about we just say we're going to enumerate this x distance here, and we're going to say for the first rectangle, maybe this one on the far right, we'll call that x1, wherever it is, and then we'll move a little bit to the left and call that x2, and just counting these guys. So then the 1/2 x really becomes 1/2 x sub something. I'll just call it I. So that's just our way of kind of naming these things. We're just going to think of them going from 1 to n. But I said I wanted the area of all the rectangles, and so I think it's safe to say, hey, we're just going to add the areas of each individual rectangle. And so that's what our sigma notation does. And we're going to start at the first rectangle, and we're going to go up to, and then we'll just pick the letter n. That'll be how many rectangles we have. And then what do I do to get better and better approximations for the area of that triangle? Limit as n goes to infinity, right? We want more and more rectangles. So then we're going to say the area of the triangle is equal to, I'm going to leave a little space, and then I'm just going to copy that sigma thing there. And then inside of that space, what did we say we were going to put? Limit as n goes to infinity. There you go. Yeah, the base and the height we're given is 3 and 6. I'm not saying this is a useful way to find the area of that triangle, but the process is going to be one we can extend to all sorts of problems where we don't have a nice little formula like we did for the triangle. Okay, so that thing right there is called the Riemann sum. That's what Ryan read up in the top. Riemann was the name of one of the early calculus guys. And hey, look, it sure reminds me an awful lot of what's on the whiteboard here, right? I see a limit, I see a sigma, I see a delta x. Really the only question is, what's this blue underline thing, this f of x sub I? What is it in this example? Is 1/2 xi, right? That's it. Everything else looks exactly like this thing on the board, which means that I can rewrite that thing on the smartboard as an integral from something to something. All we're doing is changing the f of x into what we just said, 1/2 xi, or 1/2 x, we should say. So we're recognizing that this guy in blue on the board is really your f of x sub I. And everything else looks exactly like the thing on the board. And so that gives us the right to change it into an integral. Again, on the board, f of x is what we put. What are we putting here? 1/2 x. Just notice that the I dropped out. It just became x instead of xi in the integral. What happens to the delta x? It becomes a dx. The limit and the sigma both become the integral. The only thing that doesn't appear in our crazy notation here are the limits. So this is where we have to physically think about taking that rectangle and sweeping it left and right. When you pick the smallest x possible, that puts me at the far right. What's the smallest x we could start with? 0. And then if I take this guy and I branch all the way to the left, what's the biggest x? Is 6. So that's really the only place, the only thing you have to bring in that isn't part of all the sigma and limit stuff. Okay, super. And we've written now the area of that triangle as an integral. Most integrals are really hard, but this one happens to be easy, so we'll do it. So the A and the B don't appear any place in the sigma notation. So you would have to just have it in your picture and keep track of it so that when you went to the integral, you put 1 and 3. There is, we were quite loosey-goosey when we said just 1/2 x sub I, but if you were a little bit more precise there, you could actually come up with a formula for the x sub i's, and that formula would involve, say, going from 1 to 3. We just kind of waved our hands and said, oh, x sub I, we know where it is. We don't have to be precise. Okay, so let's do the antiderivative here. So what do we get? 1/2, so then it becomes x squared divided by 2, going from 0 to 6. Yep. Let's see, 6 squared is 36, divided by the 4, minus 0 divided by 4. 9. Yeah. You could think of any integral as being rectangles underlined, but we're going to do in number 3 a volume problem where it's not going to be 2-dimensional rectangles, it's going to be 3-dimensional things. Yeah, we've got a third axis here in number 3. Okay, so let's give this a shot. All right. This actually is something you could find the volume of. This is part of what kind of a shape? Like half of a cylinder, right? And there's an easy formula for the volume of a cylinder. You may or may not know it, but you could use it just like we did half base times height for the triangle. But we're setting things up with this Riemann sum business, so let's give it a shot. So in this case, we're going to estimate the volume of one of these. I'm going to call it a slab, like this little guy that's kind of separated in between. It's like the thing in the middle of the sandwich here. So we're going to find the volume of one slab. Right, it's not a rectangle anymore, it's a 3-dimensional thing. Okay, so I know the volume of, okay, so that guy right there is curvy, but if you imagine it being really, really thin, then it's approximately straight everywhere. And so it's kind of like this long, narrow shoebox, really thin shoebox. And what's the formula for the volume of a shoebox? Yeah, so there are different names for it. I'll call it length, width, and height. So yes, it is. I mean, it is not straight. I mean, it's got curves, and the top part is definitely smaller than the bottom part. But if I really imagine shrinking this guy way, way down, super thin, short, then it's so close to being a square, then why should, like, let's not bother with the fact that it's slightly different from a square. And what's that? Stretch it. So I'm imagining like a piece of paper thickness of a slab here. Yeah, and it didn't bother me, right? Like this, yeah, just imagining it being straight so that I can find an easy volume. And it didn't bother me that this wasn't a rectangle here, right? It was technically a trapezoid, but we don't care, right? It's so thin, it hardly matters like the extra that you get or the extra that you miss. Okay, so same idea down here. So length times width times height. All right, two of these guys are easy. Okay, so again, thinking about that slab in the middle there. Let's say that this guy right here is the length. What is the length of that slab? It's 10. And do you buy that it's 10 for all of these slabs? Imagining slicing this guy everywhere. Okay, 10 times. Okay, let's say that this is the height of the slab. That's a symbol, but it's given in the picture. That's the delta y. So I'm going to leave a blank there. And I'll say that we've got our two easy things there. 10 is the length. Delta y is what we're symbolizing for the width. Sorry, for the height. But the width is the tricky part. And so the width I'll draw here in blue. So this is what we're calling the width in this picture. And it changes, right? If your slabs are real high, then the width is pretty small. But as your slabs go down lower to the bottom, they get bigger and bigger and bigger, right? So it's going to have the y, it's going to have this letter y in it. Depends on how high you are in this cylinder. Okay, so I'm trying to find that distance. So I'm going to draw something else in here. I'm going to draw from here straight to here. What letter is that in this picture? That's the y, right? That picture, that's the y. And I'm also going to draw here to here, which is actually the same constant all the time. What is it? It's 7 in this case. Right? We all buy that? That's the radius. It's always 7 regardless of where the slab is. So then the W that I'm interested in, okay, well, I guess it's only half that I'm going to find. I heard some sines and cosines. We could play that game if we knew angle stuff, but at the moment I've got two sides of a right triangle. So what theorem to get the third? Pythagorean theorem, right? A squared plus b squared equals c squared. So let's do that to find this distance here. What are you finding cosine of? But y is a side. So if you're talking cosine, then you need to start getting your hands on some angle. Okay. All right. So then I think if we do that, we should find out that that this distance right here is the square root of 49 minus y squared. Is that all right? Blue thing squared plus 7 plus y squared equals 7 squared. And so what is the width then? It's 2 of those, right? 2 of those, because the root 49 minus y squared was just the blue length, but I wanted the width of the whole slab, the red, so it's double. Okay, and we're in really good shape here because pretty much all we need for this whole Riemann thing to work is that the delta letter, which is a y in this case, matches the only other letters in the problem, which is just y. Delta y what? Yeah, delta y is going to be some small number here. I don't want to say it's constant, but it's if you choose one slicing, it's constant. We'll just say it's the same delta y for every. Yeah, the width is the guy that's changing. As you move this slab up and down, we can think of the heights as being the same. We just make that choice. But then the widths change as your slab goes down to the bottom or up to the top. Yeah, the length, we kind of got lucky that it was constantly 10 here, but you might have y's inside of there too, right? If it changed in two different dimensions. It's a good point. Okay, so this is the volume of one slab. How about we then find the volume of all the slabs? So pretty much all we're doing is slapping a sigma in front of this thing, right? So 10 to square root of 49 minus y squared delta y. Just saying that all the slabs have that same formula. But here we have to give ourselves a way to count all these slabs up, to enumerate the slabs. So I've been using the letter I. It goes in exactly one spot in this expression. It goes right there. Yeah, the delta y is just the same number all the time. It's really the y values that are changing. And then we can just always go from 1 to n. That'll just be our standard. And so then we take the volume of the actual solid. We were just approximating, but now we'll get the right answer. So I'm going to be a little bit lazy. You can be lazy here too. This thing gets copied down, but what goes in the front? Limit as n goes to infinity. So that's our way of saying, okay, we're going to make these guys not just paper thin, but even thinner than that, right? And the more slabs we have, the better the approximation. And if we have infinitely many slabs, it's perfect. Okay, but now that guy looks an awful lot like the thing on the whiteboard. And so we get to change that crazy complicated thing into an integral. So this equals integral. I'm going to copy everything in there, very small changes here. 2 square root of 49 minus one little change here. It was y sub I squared. Now it's just y squared. It was delta y. It's now dy there. And then there is one little thing you got to think about here, and that's the limits. So you really do need to look at the picture. So y is this vertical change here. So smallest y up to biggest y, 0 to 7. Okay, now that integral is not impossible to do, but I don't want us to get distracted by it this class, so we're just going to type something into the calculator here. Any ideas on what technique might work for that integral? Yeah, this is that sine theta substitution, right? See an a squared minus x squared. Good. Okay, so square root of 49 minus y squared, close that, everything, I think we're good. Comma y, comma 0, comma 7. Did I do that right? Yeah. And so as it's doing that, anybody happen to know the formula for the volume of a cylinder? Yeah, it's the area of a circle times the height. Okay, so the area of this circle is pi r squared. So 49 pi, we'll end up dividing it by 2 times the 10, right? So 49 pi times the 10, do we know this? Pi r squared h is the volume of a cylinder. So 49 pi times 10, but half of that. 49 times pi times 10, but half of that. Any guesses? Wow, you guys are just like mental calculators. That was amazing. You just did that in your head? Fantastic. Okay, good. Right. What's up with that 0.06 at the end? So this is the answer we should have more faith in, the 0.011, because that's the volume of a cylinder, right? But anytime you ask the calculator to do calculus, you are throwing caution to the wind because the calculator knows zero calculus and it just approximates everything. And it literally did our integral by thinking about rectangles, and maybe it used 10,000 rectangles and it should have used a little more. I know. All right, next page. Number 4 talks about this last problem, which involves a new kind of solid. which is solid with known cross-section. You'll see why we call it that in a second, but there is this warning. These kinds of problems are typically quite hard. So number 5, Brendan. Okay, let's pause there. So we got a circle. So just we're going to draw stuff in a second, but let's just imagine before we draw. So you got the circle, x squared plus y squared equals 4. And you're going to draw above the piece of paper, right? Your circle is on the paper. You're going to draw in this third dimension here a bunch of squares. And these squares are going to be perpendicular to the x-axis. But you're not going to draw any old squares. You're going to draw a square so that it is exactly the right height so that it would have come from that circular base to start with. So imagine that circle. If you are at the far right-hand side of the circle, there's nothing to draw because you don't have, I don't know how to say this. I'm just going to draw. Yeah, like the squares have to come from the circle. And so it's not a sphere. I'm going to erase this in a second. But you're going to imagine squares coming out of the board at you, but you got to have squares that are the right height. And so, for example, there's a square of this height coming out of the board right there, but coming out of the board here is a square of a bigger height. Yes? And then coming out of the board over here is this cute little tiny square because it doesn't have much of a base to come off of. Right? So kind of dome-ish, right? It's going to be small and then big and then small. What's that? Well, so I mean, it's going to be big in the middle and small on the extremes here. But what it really looks like, it's kind of hard to draw. So so I'm just going to do my best here to draw. We're going to lay. All right, so that's my x-axis as normal. But I'm going to draw the y-axis into and out of the board, just kind of lay it flat. So there it is. And now we're going to have our circle. The circle kind of becomes like elliptical looking when you sort of lie it flat. So 2 and 2 and -2 and -2. And now this is the part where it gets hard for me. So we're going to draw just a few slices, like there's one there, and I'll draw a few more. So coming out of the board here is a square, and the square's base is in the circle. So that's a fairly small square coming out of the board at you. And then we will draw in another color a square with that base. And that square is going to be bigger because it has a bigger base. So coming straight out of the board, going up exactly the right length. How's that? Bigger square there. Where's the biggest square? Right in the middle. And then as we go to the right, they have smaller and smaller squares. So that's the volume of the thing we're trying to find. Did somebody say why? Because we can. That's why. That's fine. But let me show you a picture, a nicer picture. So this is what it looks like here. And we'll find its volume in a moment. But you can see the circular base down there with a bunch of different cross sections here. And can you see all these black squares? Small ones in the front, bigger, bigger, bigger as you go to the middle, biggest ones there in the middle, and then smaller on the other side. And we have these kind of, did you guys see this? That there were going to be like these two like straight kind of things, two sort of pointy parts of this thing. Yeah, so it's like cornered, but it's just curves. I don't know. Yeah, we're changing in 2 different dimensions here. Yeah. The center one has a height of 4, I would say. Height of 4, yeah. Okay, so let's give this a shot. I'm going to draw one more of these guys here just so I have somebody in the positive spot. Okay, this point right here we're going to call x comma y. Just some generic spot, some generic square. What we are going to do is imagine taking this shape and we're going to cut it into these cross sections, the square cross sections, a few of which are drawn here. And we're going to give those cross-sectional squares just a little bit of thickness, just a tiny little bit of width, so it's going to be a 3D slab, right? And then we're going to add the volumes of those slabs and act surprised when it's an integral. Cooper? Because the base in the middle from top all the way to bottom is how long? 4, right? And so it's got to come all the way out 4. Okay, so the goal is to find the volume of one slab as usual. Okay, so slabs are base times width times height, or length times width times height is what we used before. Yeah, two of these guys are the same. Okay, so let's just name the width of this thing. How about delta x for the little thickness? I'm not going to add it to the picture, but delta x is this little thickness that these squares are going to be given. So that'll be our width. So delta x there, and then we got to find the length and the height. And as Rob points out, they're going to be the same. But what letter do they have to be a function of? X, right? I have a delta X. The only other letter I'm allowed in here is X. Okay, so that's a problem for us because, what color can we do? Green. So we know that the area of that square is is the green thing times another green thing, right? Okay, but is the green thing here, would you call that something with X or something with Y? X and Y, yeah. So Y is this distance here. So how much is green? Green is 2Y. You buy it? Right? It's just twice that vertical. Okay, so if I were allowed to, I would just put 2y in both of these parentheses, but I'm not. So we need to get it in terms of x. So yeah, that's the equation that relates the x and the y, right? So solve this equation here for y. And it looks just like the Pythagorean theorem calculation. Mm-hmm. It would be. Mm-hmm. Okay, so then I think we're good to go here. So what are we putting in the first parentheses for the length? It should have been 2y instead. To that stuff, right? 2 root 4 minus x squared. It would be. That's I'm just writing it out so that people see all the pieces, but square away. Mm-hmm. Everybody see where the pieces came from? Okay, yeah, and Alex has a good idea to clean this up a little bit, right? So 2, 2, 4, and then 4 minus x squared. Right? The square root goes away when you multiply it by itself. All right, that's good. That's the volume of one slab. And now what are we going to do? We're going to take a sum of all the slabs, right? That crazy shape that we certainly don't have a nice formula for like we did on the cylinder or we did on the triangle will still yield to being approximated by a sum of all these slabs. So volume of all slabs is the sum of this formula, 4 minus x squared dx, going from I equals 1 to n. And remember, the I does come in to that formula, right? Where does it go? Right on the X, right? So that should be XI. That's just us numbering all of these slabs. So let's see, going from 17 to n. I guess as long as you still have a limit going to infinity, then we'll end up getting the same integral at the end. Yeah. Yeah, it's just a numbering convention, and typically we started at 1, but the important thing is that we're going to infinity. So I think even if you started calling it 17 to n, it would still be okay, still the same. Okay, so then the actual volume, I'll just write actual here. I don't have a good name for that crazy shape. So the actual volume is going to be exactly that, but with what in the front is our limit. And goes to infinity of all this stuff. And then once you've got that stuff written down, see if you can use our favorite thing on the whiteboard here to rewrite that as the corresponding integral. So the cross-section ones, you are probably going to have to generate the picture as the first step. Mm-hmm. Yes, cross-sections are the kind of limit to what we can do. Okay, thinking about sweeping these squares left to right. How much is x at the far left? -2. Isn't it -2 at the far left? Right? And then how much is x at the far right? Is +2. So that's the integral that we need to find. -a to a. So there was a law that this was equal to 0, but that was only for a very special kind of f. It's the other one. Yeah. If f has a certain kind of symmetry where you cancel some positive stuff on one side with negative on the other. Yeah. Okay, right. So this integral, I actually don't even care what the answer is. I mean, you can find it by hand. It doesn't take that much time. But the important thing for us today was getting to the Riemann sum and converting. Okay. So basically, what we've discovered here is this really nice formula. Is that if you can find a function that represents the area at a generic x, just like we had the area of the square at a generic x, then you throw that formula, that function, into an integral, let that cross-section just kind of slide through the region, and you will have the volume after you do your integral. And yeah, got to get everything in terms of one variable. So you can check this process out during the activity, which you're going to start right now, but basically, yeah, part of it is this function of only one letter. So there's the process. Activities start on the next page. Feel free to refer to these examples in that process as you work together here. Yeah.